Hello everyone, welcome to my course in college algebra. I've been planning to do this for a while now, and I've kept hitting a few hiccups on how to proceed with these lessons, but I think I've figured it out. Before getting into algebra, before getting into college algebra specifically, I want to do a set of lessons on the prerequisites of algebra. These lessons will be considered what will be taught in an Algebra 1 class or maybe an intermediate algebra at a college or a community college maybe. So without stalling any longer, we'll start with chapter 1, properties of real numbers. In this section, we are going to study sets and what sets tell us about the math that we're going to study in future courses in algebra and beyond. Sets are a unique way of describing the numbers that we use. They're a way of categorizing numbers that make it easiest for us to manipulate and handle. With sets, sometimes we can visually see what we're dealing with in math. If you've never taken algebra before, all the math that you've worked on would have been just simple arithmetic: addition, subtraction, multiplication, division, fractions, decimals, maybe some applied math. If you were in grade school, you would have studied telling time using math or counting money. Now, as you move higher into the types of mathematics that you learn, it becomes much more easier and sometimes a requirement to have a set of numbers. So, for example, a set, say we have a set of cars that we own, and we want to talk about the three different cars that we own. Each car is a different color. So, say we could have a set named C, C for cars. In this set, we are going to set it to equal a bracket and a closed bracket. And then you will put your information inside, separated by commas. For example, the set of cars that we own, set C. You can name a set anything you want. So set C, and we have red, green, and blue in closed bracket. Now we have a set containing the three colors of the cars that we own. We have a red car, a green car, and a blue car. That's all that sets are. It's just a way to describe what we have in a specified group. Say, for example, you want to say the numbers 1 through 6. We have a set, so since we're using numbers, let's use a set called N. And you wanted to say in this set, it's numbers 1 through 6. So you write 1, comma, 2, comma, 3, comma, 4, comma, 5, comma, 6. Close bracket. That's a set. So sets is just a group. It's a group that we can use to visually see what we're dealing with, what kind of numbers we have in our group, etc. And you'll find that there's lots of different ways that we can use these sets when you move into more further mathematics. But for now, for these courses, you're going to want to know sets so we can see what numbers we need for certain situations. Sometimes you'll have a set with nothing in it. You could simply make a set, let's call it S, S for set, and you could just have an empty bracket. That's a set with nothing in it. What if I wanted to say that something is a part of a set? What if I want to say check this out. We have this set N right here. Let's get the white marker so I can contrast it. We have set N. Let's work with set N. And what if I wanted to say that 4, this number 4 here, is a part of my set N? I will use a new symbol. So we've used the plus for addition, the X for multiplication, etc. We're going to learn a new symbol. This symbol is called the element symbol, and it looks like a curvy E, or like a C mixed with the capital E maybe. That's our element symbol. So if I wanted to say that 4 is an element of this set, I could write 4 is an element, and then you would write the set 1, 2, 3, 4, 5, 6. Close bracket. 4 is an element of that set. You could also write it as this. 4 is an element of n. So sometimes it gets too tiresome. You don't want to write the whole set. Sometimes these sets can get big, really big, as you'll see when you study matrices and further mathematics and linear algebra. You'll find these sets can get quite overbearing. So you don't want to write the whole thing every time. Now, notice I don't have 7 as a part of the set. What if I wanted to say that 7 is not a part of n? Easy. Just like how you have the not equal sign, we have the not an element sign. So I could write 7 is not an element of n. If I wanted to say 2 sets are equal, you could do the same thing. Say if I had a set of 3 and 7, I could say that's equal to the set of 7 and 3. The order that these units or elements appear in the set is not important. All that matters is that the same elements are in each set. So 3 and 7 is equal to 7 and 3 in both these sets. And we can do the same thing for not equal. We can say that 0, 3, and 7 is not equal to 7 and 3 because one set does not contain the 0th element. Now, in algebra, we don't use just numbers. One of the big learning curves of algebra is knowing that some numbers are not known or unknowns. In modern times, we call these unknown numbers variables. If you have older math books, they would be known as unknowns. I have a few math books. One actually uses unknown for that. So let's say we have a number x. This x is a number. It's not a letter. It's a number. We just don't know what it is. Let's say that x is somewhere in between 3 and 7. We have a unique way of writing this. There's a system called set builder notation. This system allows us to describe what a number may be. It's also used for other things, but we're going to start with the simpler things. So say we have this variable x. What is x? We don't know. So we're going to say x such that. Let's put everything in brackets. X such that. This line means such that. We are talking about x. X such that x is between 3 and 7. Close bracket. That is set builder notation. X such that x is between 3 and 7. That literally defines a set. 3, 4, 5, 6, 7. That defines a set containing the numbers 3, 4, 5, 6, and 7. This set is x. X is somewhere in between here. So, this x is the element. All elements of x. So we are looking at all elements of x. That is this. So x, all elements of x, such that x is this. That's how we read set builder notation. This, who knows what this could be? It could be is between 1 and 2, between 2 and 3. Whatever we need for that situation. In this situation, it's between 3 and 7. A more definitive way of writing this, we have x such that x has some property. X such that x has some property. Whatever that property is can be defined by the situation that arises. So let's look at a few examples. I am going to write a set in set builder notation. Say I was asked to list the elements in a set. So you would be giving a set and set builder notation. Such a set may say x such that x is less than 5. So list all the elements in the set. X such that x is less than 5. What are the elements of the set? All numbers less than 5. So you would write x is equal to 1, 2, 3, and 4. And there's your set. Because if you're less than 5, you can't be equal to 5. So all the numbers is 1, 2, 3, 4, and 5. We're not working with 0 yet. 0 is a part of a different set. I'll explain that shortly. Let's do another example. Let's say we have a set where we have x is equal to 2, 4, 6, 8, and 10. Say x is equal to 2, 4, 6, 8, and 10. How do I write this in set builder notation? You would write x such that x is the first 5 even numbers. Close bracket. Simple as that. We're just describing the numbers that we have. All right, so let's check out some common types or sets of real numbers. So the numbers that we use are categorized in unique sets that we use in everyday life, especially if you're in math class. So the first one, which is what we get our title for this chapter, real numbers. What are real numbers? Why do we have to say real? Are they fake numbers? Not fake numbers, but they are definitely other kinds of numbers that are unique compared to real numbers. Later on, in a deeper section, we'll study what's known as complex numbers, sometimes called imaginary numbers. And the cool fact, negative numbers were not always thought of as real numbers. Some people even call them fictitious numbers or numbers of fiction, which is really unique. Now, negative numbers are considered real numbers. Not the square root of -1, though. So, real numbers. What are real numbers? Real numbers are all numbers that we encounter in everyday life. They're the numbers we use in math class. They're the numbers we see on a calculator. They're the numbers we see written in the pages of a book. They're the numbers seen in your bank account, positive or negative, whatever it may be. Those are all real numbers. Real numbers are 1, 2, -3, 1/4, 2 + 4. Those are all real numbers. There is a special letter when we use real numbers in a set notation. This symbol is a letter we usually use the capital script R for all real numbers equals all real numbers. All real numbers, capital script R. Remember that. You see a capital script R, or capital cursive R, we are talking about all real numbers. What are natural numbers? Natural numbers are usually denoted by the capital N for natural. Remember, R is for real, N is for natural. The natural numbers is every number greater than 0. So we have 1, 2, 3, 4, and all the way to infinity. All numbers greater than 0. What if we wanted to include 0? Well then, let's talk about whole numbers, usually denoted with the W. This includes all positive numbers plus 0. So we have 0, 1, 2, 3, all the way on to infinity. Easy, right? Why is 0 not included natural numbers? Well, 0 is not there. If you don't have nothing, if you have no apples in the basket, there's nothing there to count. So it's not a countable number. Natural numbers are your countable numbers. You can count these numbers. You can't count zero. If you have 0 plus 0, what is 0? 0 is nothing. So there's nothing to count. So natural number. Think of natural numbers as counting numbers. They're counting numbers. The numbers we can count. So what about integers? What are integers? Integers are not written with the I. They are not happening. They are written, ready for this? Z. Really unique. The Z comes from the German word for Zahl. I think I said that right. Zahl, Z-A-H-L, and it means number in German. That's all it is. Literally means number in German. We run out of English words, so we gotta use words from other languages sometimes. Why do you think we use a lot of Greek in algebra? So, we have the German word Zahl, meaning number, for integer. What are integers? Integers are all numbers on both sides of zeros. So we have 0, 1, 2, all the way to infinity. And from 0, we have -1, -2, all the way to negative infinity. Bear in mind, it's not important right now. It will be important when we hit calculus. Infinity is not a number. All we're saying that as these numbers continue to grow, they get bigger and bigger and bigger. A million is a big number, nowhere near as big as a billion. A billion is a big number, nowhere near as a trillion. You keep getting more. All infinity means is it keeps getting more bigger and more bigger. It keeps going. Same thing with negative infinity. Negative infinity doesn't exactly mean smaller and smaller. It means negatively bigger. Negatively bigger. A negative million, a negative billion, a negative trillion. That's all that means. So don't treat infinity as a number. Get that down now. It'll be a lot more easier when we hit limits in calculus. All right. Rational numbers. I love rational numbers. Most people don't like rational numbers. Rational numbers have some unique things in algebra that get really fun. So, what is a rational number? It dictates a ratio. Oh, box this little part right here. Ratio. A ratio is a rational number. 1/2 is a ratio, rational number. 3/4. 7/11. Those are rational numbers. All there is to it. It's a fraction. It's a rational number. Even 3/1 is a rational number. Even though this equals 3, it still equals 3/1, which can be thought of a rational number. Another way of thinking of a rational number is an integer divided by an integer. If you can have an integer divided by an integer, then you have a rational number. You have a rational number if you can divide an integer by an integer. What if you can't divide an integer by an integer? Then you have an irrational number. An irrational number is an integer that cannot be divided by another integer. What are some irrational numbers? Some irrational numbers are pi, which is 3.14159, etc., etc. You have Euler's number. If you have taken algebra before, then you definitely have seen Euler's number, which equals 2.7182, I think, something like that. It's a number used in, it's called the natural number. Natural number. Don't get it confused with this natural numbers up here. It's not that kind of a natural number. This is not a natural number of the set of natural numbers. This is called the natural number for a different reason, which we will study when we hit Euler's number. So I'll write the guy's name here. Euler. It looks like Euler. It's not Euler. It's Euler. Sounds like oil, like Euler, it sounds like, but it's Euler. So, you have E for Euler, obviously. That's the best way to remember it. Euler came up with that number. Um, Another one is phi, which I don't remember. I know it's a golden ratio. I don't remember the number off the back of my head. You have the square root of 2 is an irrational number. And so you find that basically an irrational number is a number that cannot be divided by an integer. There is no number divided by a number that gives us pi. There's no number divided by another number that gives us Euler's number. That's all that irrational numbers are. I think we're about halfway through. All right. So the real number line. This is when we start being able to manipulate these different things. Once we have an idea of what numbers are, how to read them, we have we have set builder notation and whatnot. We can actually start looking at numbers geometrically. In other words, how they represent with each other on a line. As of right now, all we have is the one-dimensional line, the real number line. Soon we will have the Cartesian field, and then one day we'll be able to do the 3D field, and then many other fields after that, after you get into all kind of other numbers of math. So, parts of the number line. We have, first and foremost, the origin. The origin is the point 0. Not all number lines will have 0. Some number lines do, some don't. It depends on the situation. If you're working with numbers between 100 and 1,000, there's no reason to have 0. You're going to start at 100 and you can end at 1,000. If you work with numbers from -10 to 10, then you'll have 0 because 0's in the middle. It's included. So it just depends. Don't get freaked out if you see a number line that doesn't have an origin. You may not need it. What about all these other points? We have 1, 2, 3, -2, -3. Those are called coordinates. Those are the coordinates of the number line. They're the points of reference for each number that we are using. Not all coordinate points will be marked. We have 0. We got skip the coordinate point. 1, skip the coordinate point. 2. Sometimes you're not going to want to see 1/2. That's a 1. 3/2, 5/2. You're not going to want to see that written on a number line. It's cluttersome. So sometimes you'll see number lines with missing points in between to help us know or see the half point between each documented or noted point. And so if you know the number you're looking for, you can find it on the number line. Say you're looking for the number 7. Say we need to find 7. Pick a point. Let's mark it 0. There. We set this point here to be 0. I don't want to use any of those colors. Let's use blue. 0. There we go. 0. So we got 1, 2, 3, 4, 5, 6, 7. There's 7. Easy as that. Let's erase this. Say we want to find 50. Say we want to find 50. Let's mark this over here as 0. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So there's 50. Now that's kind of cluttersome. You did not have to write all that. We could have left out the 5, the 15, the 25, the 35, the 45. We could have left all those out and it would have made perfect sense. So that's all it is to finding numbers on the number line. Not hard at all. Negative numbers. Negative numbers are fun, but can be really tricky. So what do we have with negative numbers? A negative number is simply toward the left. Where my mouse went? We have toward the left of 0. And they're denoted by a minus sign. When you see minus, you're dealing with a negative number. So if we have 3 minus 2, what you have is a positive 3 and a negative 2. That's what you have. So anytime you have a subtraction, you're dealing with a negative number. the answer might still be a positive number, but you're still working with a negative number. So all negative numbers are to the left of 0. What about the additive inverse? What is that? All the additive inverse is for every number A, you are guaranteed to, I feel like I'm hiding behind this mic. You are guaranteed to have a negative number A. So any number over here on this side, on the right side of 0, you will have the inverse of that number on this side of 0. So if you have a 5, you're guaranteed that there will be a negative 5 on the other side of the 0. If you have if you have 1,000, you are guaranteed to have a negative, I don't know why I'm using equal sign. You are guaranteed to have a negative 1,000 on the other side of the 0. That is your additive inverse. Every number will have an inverse. So if I asked you what the additive inverse of 3 is, you would tell me that the additive inverse of 3 is negative 3. That's all it is. What if I asked you what the additive inverse of negative 2 was? What is the additive inverse of negative 2? Well, if you remember your math, a negative and a negative always gives a positive. So the additive inverse of negative 2 is 2. Because remember, negative of negative 2 equals 2. It's called, that is called a double negative. Sorry for my handwriting. Double negative. A double negative is the additive inverse of a negative number. It gives a positive number. So, like I got this number line down here. So if I asked you what the inverse of 3, you would say it's negative 3. And if I asked you what the additive inverse of negative 5 was, you would say 5. All it says is that each number A has its inverse. Absolute value. Absolutely difficult to work with sometimes, especially if you're not used to understanding this type of math. Absolute values gets really difficult for me. It was really hard for me to, sometimes still is, to kind of figure out what's going on. Intuitively, it's very simple. It's very simple, but it can get very complicated very fast. All right, so absolute value. What is absolute value? Absolute value is simply a number's distance from 0. How, not who, how, oh, come on. How far from 0? How far from 0? That's how it is. There's a definite, I'll write the definition shortly, but my cat is watching my the YouTube channel. So, how far from 0 a number is. So let's mark 0 right here. How far from 0 is 3? 3 is 3 units from 0. How far is negative 3 from 0? I gotta move this. How far is negative 3 from 0? Negative 3 from 0 is still 3 units from 0. So, both of these, negative 3 and 3, the absolute value of negative 3 equals 3, and the absolute value of 3 equals 3. So we notice that no matter what side a number is on, the absolute value of a number and its additive inverse is the same. How do we write that? So, first and foremost, we have a number 3. To write it in absolute value form, you just surround it with 2 brackets or 2 bars. That is the absolute value of 3. So if I put absolute value negative 3, that equals 3 also. So what is our definition? Our definition is the absolute value of a number, let's pick A, equals what? It equals A if A is positive or 0. And it equals negative A if A is negative. What? That used to throw me off so bad. That was difficult for me to grasp. The first part of this equation is super easy. A is equal to A if it's positive or 0. So, for example, we have absolute value of 3 right here. That equals 3. Absolute value of 5 equals 5. Absolute value of 10 equals 10. Cool. What is the second part saying? Absolute value of A is equal to negative A if A is negative. Let's write it out part for part. We have absolute value of A is equal to negative A if A equals a negative number. So A is equal to negative A. Let's follow this out. We have negative A equals a negative A. This negative right here is not part of this A. Remember that. A right here is being shown that is equal to negative A. So what we have here is a double negative. Please leave comments if you are not following this. I will try to do a follow-up video with nothing but absolute values to try to help solidify this, because we need to know absolute value if we're going to move on into other mathematics. So, what this is saying, the second part of this definition, absolute value of A is negative A if A is negative. In other words, the absolute value of A is a double negative if we are taking a negative number. So, this right here, we have negative A. So what we have is negative A. What is A equal to? Negative 3. So we have negative 3 equals 3. That's all it's saying. Carry out that negative. Don't think that this negative, bring it over here. Don't think this negative is the same negative if this is negative. I hope I'm making sense. Let me know if I'm not, please. So, absolute value. What we are saying, let's check this out on the number line. Geometrically, when we are looking at it on the number line, when we are looking at these examples on the number line, we are analyzing this geometrically. So, absolute value of 3. Why did I use a parenthesis? Of 3 equals 3. So, when we have absolute value of 3 equals 1, 2, 3 units from 0. Absolute value of negative 3 is 1, 2, 3 units from 0. The definition might be a little strange, but all it wants from us is how far from 0 are you, whether you are a positive or a negative number. If you think of it that way, you can't go wrong. Inequalities can be really confusing for a lot of people. A lot of people have seen it written as the less thing being similar to an L, so equals less than. A lot of people think of it that way. Or the mouth eats the bigger number or something like that. So the bigger number is what you always want to eat more food, so you gotta eat the bigger number. I've always seen it like that. Gotta break away from that. It's great in the elementary school and whatnot. It's time to move on. You're gonna have a lot of things where that's not going, that this type of ideology is not going to help you. You're gonna be involved with writing proofs and different things, and having that kind of ideology is gonna be kind of difficult. At least for me. Maybe it will work for you. I don't know. But it don't work for me. So I don't like that. I just memorized what the symbols mean. So we have 4 symbols. 4. We have greater than and equal to, less than, and less than or equal to. That is the four symbols we have with inequalities. So say we have, let's go in the number line. We have 0 right here. Let's mark our origin. Say we have 3, 1, 5, -3, 8. And we got some numbers written down. So let's look at some of these numbers. Reading inequalities algebraically. I can't read at all today. So let's use number 3. Compare these other numbers to number 3. So 3 is 3 greater than or less than -3. It's greater than. We have, no, I was going to erase that, but I'm not going to. So we have 3 is greater than -3. What about 0? 3 is greater than 0. What about 3? Is 3 greater than or less than 3? 3 is equal to 3. 3 is less than 5. 3 is less than 8. This is like super easy stuff. Super easy stuff. You could have also written 3 is greater than or equal to 3. Because technically, you're right. 3 is greater than or equal to 3. You have that or in there. That or counts as the equal part. I keep getting in the way of my mic while looking at the camera. Why do I do that? I have this mic that just... So, graphs. Interval notation. Graphing notation. What do we have? We have information that we want to graph on a number line in certain ways. I might need more number lines. Alright, so using interval notation, we have what's known as open and closed intervals. Let's do open interval and closed interval. Alright, how do you write these algebraically and geometrically? Alright, so you may have, if you've taken math before, if you've taken different college maths before or worked with graphs, you may have seen points of a graph marked as some number and some number. That's normal. You'll see that all throughout all math classes. However, when we're dealing with intervals, this here has a meaning, and you can't just use that whenever you want. So, what's that meaning? An open interval that is used, don't use the same color, that is used with the parentheses A and B. What this says is that we are including both numbers. We are using an interval. Let's put it this way. Say A is some number over here, and B is some number over here. Remember algebra, we can swap numbers with numbers. We can swap numbers with letters without any importance of knowing what that letter or what that number really is. So, A is some number over here, B is some number over here. Say we want to use interval notation, we use those parentheses. Let's write the A a little further down, the B a little further down. And you draw that line in between them. That means every number in between A and B is included here, except A and B. Open interval does, learn how to spell maybe, does not include the mentioned number. So, closed interval, however, let's get another, I am going to need another number line. So let me get another one real quick. Bring that up here. All right. A closed interval does not use these parentheses. They use brackets. So we got A and B. So if we have some number A and some number b, we would use brackets on this number line with the line in between to indicate that we're talking about everything in between, including a and b. So we have includes the mentioned number. So there's another way of working this or writing this. Remember the remember inequalities. So say we have some number x. Let's use a different color. Let's go orange. Say we have some number x. Where is x in this open interval? X is between a and b. So that means, let's go down here. We're gonna go down here. So x is between a and b, right? So we are using open intervals. Let's start with open intervals. We have open a, open b. So x is between a and b. How do we write that with inequalities? We know that x is greater than a, but we also know that x is less than b because we have a. How do we know this? Because a is less than b. A is less than b. X is somewhere between a and b, not including a and b, because remember, we are working with open intervals. So a is less than x. X is less than b. That's how it's written. That's how this interval notation is written using inequalities. X is between a and b. X is greater than a, but is less than b. Because b is greater than a, x is greater than a, so therefore x must be between a and b. Closed intervals. Closed intervals, x is between a and b. We are using brackets a and b. So closed brackets, x is in a and b is included on the interval. So x is greater than or equal to a. X is also less than or equal to b. So we write this in interval notation. A is less than or equal to x, which is less than or equal to b. Interval notation is really useful in describing where numbers on a number line can be applied to certain equations, and this will become very important in the next few chapters of algebra. Very important, because some equations, we all know you can't divide by 0, right? If there's an equation, say we have some kind of equation, say x plus 1 over x minus 1. Say we have some kind of equation like that. That's called a rational equation, and we'll get to those one day. For now, what if we wanted to know what values of x this equation is true? Because we cannot divide by 0. Remember that, right? That should have been taught since the earliest math classes. We cannot divide by 0. Of course, we know that if 0 is equal to 1, if we know x is equal to 1, but just by looking at this, we know we can't solve the equation. So, but point being, using number lines or interval notation, we can write out what makes this equation true or false. So interval notation is very important for mathematics. Very important. You need to have this down pat. You can also write this out. This is a little freebie, because I want to make sure I include all forms of notation throughout the study. We can also use set builder notation. Say I had, let's get another number line. Drop a number line in here. I wish you could legit drag and drop it. That's fine. Say we have, let's get another marker. Let's go for yellow. Say we have x. such that x is greater than or equal to 6. How do we write this on the number line? Let's mark our origin, just because. So let's find 6. 1, 2, 3, 4, 5, 6. Here is 6. So x is greater than or equal to 6. Are we using closed intervals or open intervals? We are using closed because x is included. Or 6 is included, I should say. So x is greater than 6. So we're not going this way. We are going this way. So we're going to use a closed interval. Let's get another marker. Let's get a closed interval. And an x is simply just greater than 6. That's all we know. X is greater than or equal to 6. So we can go on and on and on. Draw an arrow. That way we know it goes on for infinity. Simple as that. Really cool, huh? Check this out. What if we had x such that, let's see, -2 is less than x, and x is less than or equal to 3. Check that out. We just mix matched. Yes, you can mix match interval notation like this. So check this out. Let's mark over 0. We know we have a -2 and a 3. Let's find these 2 points. 1, 2. There's -2. 1, 2, 3. There's 3. Cool, right? So cool. Check this out. We have x is greater than -2. That's all we know. X is greater than -2. Let's get another marker out. Let's go with purple. X is greater than -2, so are we using open or closed intervals? That is open because -2 is not included. So open interval. Oh, that needs to be a little thicker. I can't even see that. That's almost too thick. So x is greater than -2, but less than or equal to 3. So that's a closed interval. I don't like purple. I won't be using purple again. So x is in this interval between -2 and 3. It does not include -2, but it does include 3. Let's go a little further. Let's write this as a set. So let's call this set S equals, let's put the set that x is a part of. What is the set? Do we have -2? No, it's a closed interval. It's an open interval. So we have -1, 0, 1, 2, and 3. That is our set. So you can also write the set from this information. You could draw it on the number line geometrically, and you can also write the set algebraically so we can know what we are working with. So that was the first lesson. Let me scroll back over. There was a lot of scrolling. So that was the first lesson, the real number system. Moving on from that, we're going to get a little bit more work into the amount of mathematics that we'll know that we need for algebra. And when we do start algebra, we'll start with equations, and then we'll get into circles and knowing how to graph these things on the graph. And so it'll be cool stuff. But first, we need to get these prerequisites down. Simply because I just feel like I need to do it. I'll feel incomplete if I skip prerequisites to college algebra. So, with that said, I will try to upload these videos regularly. It might not be regularly, but I will do my best. Leave comments. Tell me if you think I missed some ideas that I could have put into these videos. Do you see any type of ways I can to improve these videos? Let me know. I hope you enjoyed this video, and I will see you next time. Bye.